So hi everyone, so we've just pushed the first coursework, it's on the repository. You can have a look at it, maybe start it even. So you might not be able to do everything today because we haven't seen all of the big ideas that we use, but throughout the weeks, you'll hopefully be able to make some progress. So there's some important advice at the beginning that I advise you to read. Telling you that not all of the easy marks are at the start, some of them are later in the final. So if you feel discouraged by a harder question, don't hesitate to move ahead and solve some further questions. And then you can maybe come back to the harder ones after you get some advice in the labs, for instance, or after we saw the notions in the lectures. And then you feel like you understand what the question is even about.
Right. Let me also remind you that this is a coursework only class, right?
Yes.
So you shouldn't expect to get 100% in a coursework only class, except you work very, very hard, right? So don't be discouraged if you're not getting all of the marks, and try to aim for as many marks as you want. But
I'm also kind of astonished that this appears to be a coursework designed to give you bad flashbacks to CS 106.
So, as is mentioned in the comments, the imports are important. There's a very specific list of things we're mentioning in the import lists, and so that hence that you will probably need these functions somewhere. So instead of implementing everything from scratch and struggling by just case splitting all the time and trying to solve the goals one by one, try to think at the higher level how you can combine functions to solve your problems. For some of the things, you will need to do some case splitting, but it's not always the case that just manually bashing all of the inputs is going to get you to a better state.
Yeah. So that's the bit in the James Bond movie where Q hands a random and strangely specific collection of equipment to James Bond, and you know the plot is going to require exactly that.
So then you have a bunch of topics, right? We're starting fairly easily with Boolean logic. Then we have some vector functions. We removed the one we saw during the lectures, but maybe some of them have slipped through. Then we will define what it means to be a circuit. So we have a syntax for them with some nice diagrams that tell you. I guess GitHub is not displaying monospace properly. But you get the idea, right? You get the idea. It's just to give you a sense of maybe it's a good idea to actually draw the things you're trying to build on a piece of paper on the side, and then build the program from your drawing, rather than just look at the types and try to find something that fits in there. Then you define a bunch of basic circuits. Then you define the meaning of a circuit in terms of how it transforms inputs into outputs, because the circuits we gave you are just pure syntax. And eventually you need to build CS106 building blocks and prove that they are correct this time. So you're not only testing them, although testing would be enough to prove them correct, but you also form statements that are saying exactly what the behavior of the circuit is, and then you can actually prove that it does what it says it does. Eventually, we have more complex circuits, so this is where you'll have the hardest marks, and this is where drawing will actually help you a lot, I think, because the types look horrendous, but if you know what it is that you want to build, you can slowly assemble the small blocks and then eventually produce the program. Yeah, so this one is magnificent, blockways. And then the last 20 marks are just open. You can do whatever you want. So if you want to write an add with carry, or a carry adder or a parallel adder, whatever it is that we've seen in CS106 that you really like. If you want to write a renderer to the terminal as a string or a graph, So this might look like the easiest because it's just a string you're generating, right? But it's actually surprisingly hard. So I spent a good 6 months writing the render for CSS. Do not be fooled by the fact that the type signature is simple. It doesn't mean that the exercise is simple. Or there are other suggestions, but basically you can do whatever you want. So if you have a better idea, go for it. So we have 20 marks here to give you. So the first 5 ones may be easily acquired by writing some simple extensions to whatever we gave you, but the further up you're going, the harder it's going to be to get these marks, right? All right, so I think that's it for the coursework. Oh, and the submission, I think this is the important bit, right? Where is it? It's all written in the file anyways. It's here, so you should create a private repository on GitHub or GitLab and invite us so that there's a semblance of everyone doing their own work separately. As I said during the first lecture, we'll reserve the right to ask you to come and explain some of the solutions. Really surprising. All right, and then we can start with today, maybe. So the idea was to have a look at what we did last week. So we posted some explanations on Mattermost, but I think it might be easier on a whiteboard, but we don't have a whiteboard.
Yeah, you've got one of them.
Let's try to see.
Do you
like
have
this.
something to? I can do you a notebook or something.
Do it.
Right. Also, pick a screen.
I guess we can. Oh, it was convenient to have the code actually.
Well, yeah, you can have
Yeah.
some here
Well,
somewhere.
it's hopefully visible for everyone to see. Right, so we saw this piece of code last week, and remember before we put in the solution here, everything, well, not everything, but that recursive call was yellow because Agda couldn't figure out 2 of the natural numbers. And given that there are only 2 natural numbers in this type signature, it's pretty clear it couldn't figure out what M and N are. So I think it might be useful to see how the information is propagated. So if I write...
But also look, that we do at least know the length we want in goals 1 and 2. Yeah.
Oh, I see. Okay. Right. So the codes that we have is split m equals so these m's are different, right? This is the name in the type signature. So we're saying the argument called m in the definition is equal to, and this is a pattern. So we should, I'm going to put it in a different color actually. So this is saying we've split on the second or third, we don't know which order they come in. So on the argument that's called m, and it revealed itself to have the shape suck of something. And we just happen to, okay, this is not the best naming convention, but whatever. And then we have x's as a pattern, and then what we write is let prefix suffix equals split and x's. And I do have a small screen here, so I should be able to.
Yeah.
Oh, that's good. Okay. And then the goal here is x something and then something else. So the point is that I should write the type.
Yeah.
So I'm going to write the type specialized for this clause, because when we discovered that M starts with a suck, the type itself got specialized because we got some information on that argument. So the type now actually looks something like list X suck. So it's that same M plus N. And then we return a pair of a list X suck M and a list X N. Right?
So all these lists are list M. At least that's confusing.
Yeah, this is horrible.
No, I mean the type of the.
Yeah, I understand. Right. So then how does the information get propagated? Well, we know the goal needs to have this type. So we know that whatever we're returning here is a pair of this type. So this whole thing has type, and I'm going to stop writing list.
You're off the bottom.
I'm going to stop writing list n fairly soon. So this is suck, well, my red M. And then, well, I guess the parents doesn't need to be, right? List n x n. Okay. So the pair needs to have this type, or rather we wrote it with a times here. Which means that the first component of the pair needs to have this type, and the second needs to have that type. So we learned something here, which is that the second component is list n x n. Okay, and the first one is list n x suck m. But we've already used cons to return the first value. So the remainder here, this thing, will have type list n x m. Because if we look at the type of the constructor cons here, you can see that it builds something of the shape suck of m in our case, given a tail of size m. So when we're going backwards, when you're pushing a type of size suck n against cons, we get to learn that the tail has size the predecessor of the overall length. We've managed to to figure out what the sizes of the two components should be. And so once we insert pref and sof in these holes, we have constraint propagation, so we get to learn that pref has size m and sof has size n. So therefore, this overall has size as type list x m and list x n, right? A pair of these two types. And therefore, the result of calling split should have the type list xm and list xn, which means that the two m and n's are determined because they are exactly the ones that arrived here from this constraint. So we get to learn that m and n are passed as arguments to this one.
Yeah, it's worth noting that x's has length m plus n, which might be suggestive of where the split ought to happen. But, 2 plus 2 is also 3 plus 1. So the fact that that's what it says doesn't mean that would be the only solution to the problem. So it's only when we see how the pieces are used that we see how big the pieces have to be. There was a discussion on Mattermost earlier where we could just do a little experiment of if we knock pref and stuff out of the holes again, and instead just give more of an explicit clue as to where to split. If you just as by way of an experiment. In fact, we are. So you could, of course, do curly braces, m equals m, right, and then reload, and the yellow would go away. That's enough to resolve the ambiguity. And some people might argue, given that the whole logic of this thing is to count your way m places along the input and then chop, that this might be a slightly clearer explanation of what's going on. But the other version where it's picked up implicitly from the way the preference suffer used is, it's quite cool that works.
Yeah, it's a matter of preference. So this reminded me also of when we were writing Zap here. One thing we could do, for instance, is you could notice that all of these are often the same, right? We're always returning the empty list in all of these cases. So you could swap these around and then write this instead.
Yeah.
Okay. So same, it's just a matter of preference. Now you have this kind of highlighted background here, very faint, and it's telling you that this will not be true just by computation. And that makes sense in a sense, right? Zap applied to anything and anything equals the empty list. If it were always true just by computation, this equation would never apply. So just giving you this extra hint that because of the way you wrote the function, some of the computations will take a bit more information than just what's written on the screen.
Yeah, I think we're going to see more of
Yes.
the importance of having a model in your head of how Agda will use equations to simplify stuff, and when you have to kick it.
But it's the same idea, right?
Yeah.
In terms of readability.
Yeah.
Is this more readable, or is the other version where you have a catch-all telling you, well, in all the other cases, I return the empty list more readable? It's a matter of taste to some extent, which is also why you can write it both explicitly and implicitly here.
Yeah, I wrote the 4-line version of Zap so that you would get annoyed at the middle 2 lines.
All right, so that's done. Fred, do you want to introduce propositional equality?
Can I? Yes. Right. Very good.
Right, who's doing it?
You're doing it.
I'm doing it, okay. Okay, so I'm going to show you another type, which is a very useful type. And it's something that you can't really do in Haskell. You can do something approximating it nowadays. But it's one of the things that makes Agda really useful. And it's a type of evidence that two things are the same. And you can imagine that when we start to reason about programs, then we're often interested in if things are the same or not. We would like to pass along evidence that our inefficient function has the same behavior as our efficient function, or we might want to get some evidence that the input we have is really of the right sort, or something like this, right? So, yeah, do you have anything else to add to this?
Well, not really. You're.
Nope. I'm doing fine, yeah. So let's see if we can define this. So we can't because we have a French keyboard layout.
Uh-huh. This is the reason why I let you do it.
Well, your French is probably better than mine. Anyway, so we're going to introduce this because it's evidence of something, then it's some kind of data introduction, just like lists have introduced the data of lists, right? So now I'm going to introduce the evidence of two things being equal. And I guess I'll follow the naming convention of the standard library. Is that a good idea? So it's a data declaration, and this is called equals. And we are typing this with a backslash and then equals equals. And then if you're using the Agda mode, then this backslash, which is a little bit like a LaTeX backslash if you use the LaTeX, will turn this keyboard input into this Unicode character, right? And some people on the teaching team don't like Unicode. Others like it, others are undecided.
Yeah.
But if you're using the Ada standard library, then you kind of have to get used to Unicode. Right? So we've introduced it slowly, I think. So this is the name of the thing, and you remember last time I said that underscores in names is where the argument goes. So when you use this, then you would use it something like 5 equals 3 plus 2. And you can put some brackets in here just in case.
Fair, yes.
So you see, here goes the first argument, here goes the second argument. So this would be the type of evidence that 5 is equal to 3 plus 2, right? And because we think that 5 is 3 plus 2, there will probably be some element of this type. So we have some evidence of this. Whereas the type, so this has an element. Whereas we would expect that the type 17 equals 42 does not have. So this is how we can actually make a difference, by making sure that if the equation is true, then there should be an element of this type, and if the equation is false, then we should still be able to state the equation, right? Nothing stops me from asking, is it the case that 17 is 42? And then you can say, no, it's not, because you can't give a proof of this.
Right. So this is one consequence of the kind of tighter promises you get in a language like Agda, where you really can consider type inhabitation as evidence for the truth of something. If something's not true, then you shouldn't. The type it corresponds to should be empty, and if you can point out why it's empty, then you can not have to deal with that situation. We'll see more of that.
Yeah. Okay. So that's the intuition, but we haven't actually defined this yet, right? So let's see if we can do it now. So we're going to have some, just like in list X, we had X as a parameter of the element type of the list. We're going to have some parameters here as well, namely, again, the element type of the two elements on both sides of the equation, right? So I'm going to start by saying that, well, I have a parameter X, and then I'm going to cook it the traditional way, where I'm actually making the left-hand side of this equation a parameter, so I don't have to mention it all the time. So I'm saying that for a fixed type X, and for a fixed little element, maybe I'll call it A instead, little element A of X, I'm going to have for every element of X a type. So remember that we had the list n function said that for every natural number, we had a type. And here I'm saying the same thing, that for every element of X, I have a type. It's just this time I don't know what X is. It's this parameter,
Yes.
for any X.
So what we're asking here, I mean, these types ask a question and then the values give an answer. What we're asking is, what does it mean for some element of big X to be the same as little a? When is that the case? What constitutes evidence for being the same as little a?
Okay, and I'm defining this as a data type. So I've given the type of the whole thing, right? I'm saying, well, you fix an X, you put a little a, and then for every X, we have a type of this evidence that things are equal to little a. And then I say where, and then because it's a data type, now I have to list all of the constructors, right? So all the ways that things can be equal to little a. And you could think that, well, that's really hard. But actually, because I don't know what X is, this is really easy. Because I'm going to say that the only way that something can be equal to little a is if the thing you have is little a itself. So a priori, I have a type for every X, but I only have a constructor if my second argument happens to be exactly the same as my first argument, right? They have this coincidence that these two arguments are literally the same. A here, that's the one from the parameter, A here, I've chosen to specialize this argument to just be A. Just like for the lists, I could specialize the n to be 0 for the empty list and suck of something for the cons, right? Here I'm specializing this argument to be the same as the first argument.
Right. So there's something to say here just administratively in terms of the syntax for data declarations. There's a distinction between the things which are left of the colon and the things which are abstracted right of the colon. And it is that only the things right of the colon can be specialized in the return type of a constructor. So here, big X and little a scope over the whole data declaration, and this thing here has to be little a. Those things must be used uniformly everywhere in the return types of constructors, but we can choose this thing, the thing that's abstracted right of the colon, to be whatever we like, and it happens we rather like little a.
There's also, so because it's inductive data, you're going to have it as evidence passed to you, for instance, and then you can match on it. And just like when you were matching on the vector, and when you were seeing nil, you were additionally learning that the length is 0, or when you were seeing cons, you were additionally learning that the length was starting with a sock and then being the length of the tail. Here, if you think about what it means to match on this value, it's that no matter what the indices, the parameter and the index are, when you're matching on REPL, you will additionally learn that they are exactly the same. And so it will kick off some computations in ACTA and some constraint solving that will propagate this new knowledge. So matching on this super boring constructor will actually trigger a lot of activity in the background and will bring a lot of information to the goal you're currently trying to solve. So this looks very simple, but this, as an input, it will actually be extremely powerful.
Might be best appreciated when you see some examples of this.
Indeed.
Okay, so let's do these tests that I had. So I defined this data type, and now we can see, can we prove that 5 is 3 plus 2? Right? So that means to give some inhabitant of this type. Right? Okay, so there's two ways we could do it. We could just blindly do it and say, okay, what choices do I have? Well, I only really have REPL, right? So I could just try to type that in, give that to Agda and see if Agda is happy. Or I could look at the goal and see what it is. So a priori, this is just the same, but I can try to normalize this as much as possible by doing Control U, Control U, Control C, Control comma. So Control C, Control comma was tell me the type of the goal.
What does that do actually in this case? Control C, Control comma.
Right, so I guess now I've normalized it. So
Yeah. Yeah.
okay,
Yeah.
it just works. Yeah. So I sometimes Control U beforehand does more aggressive normalization. So it's just in my muscle memory to always do Control U before you just go.
Yeah, it's just like swearing basically. Control U, Control U.
It's an Emacs thing where you
Yes.
fix Control U to something, you change the meaning slightly. And here we change the meaning slightly twice to do as much normalization as possible. So we're saying, I want to compute as much as possible. And I look at the goal again, and we see that we have computed 3 plus 2 to be 5. And now we see that this really matches what REPL can do, right? Because if I take x to be the natural numbers, because these things are natural numbers, and I take my little a to be 5, then I do have REPL, which is a constructor of 5 equals 5. So I can pass in REPL here.
Right. So it's important to get the model of what's going on here. Agda is using the equations that we gave when we defined plus. No more, no less. Doesn't know anything about algebra. Fortunately, this problem requires only arithmetic. Right? The equations we use to define plus are enough to reduce 3 plus 2 to 5. So Agda is going to get that one for us.
So maybe Agda doesn't accept anything. So we could just try to say test2 equals REFL here, right? But thankfully we get an error message in this case. REFL only works if the two sides are the same, but 17 and 42 are not the same by any equations we know, right? So it just doesn't type check. REFL does not have the right type to fit in this goal.
Right. In fact, this is a pretty confident message. Not only can Agda not see that 17 is 42, it can see that 17 is not 42. There might be situations where you could give a slightly trickier looking equation where Agda might be less aggressive in calling your bullshit.
Right, do you want to do that?
Yeah. Yeah, well, it is certainly worth doing the this particular piece of it messing up.
We have
Yeah. Well, I would do it the other way around first. Okay, you do it that way around if you like.
what did you want to do?
No, that's fine. That's fine. That's fine. I was going to have a small victory before the bad news, but now we're just going straight to the bad news. Right. Oh, is it still called? Aha, right. Mind your import lists.
I better import 0.
Aha. Right. We're in suck wars.
Oh, is it just a bracket here?
Classic.
Okay, so this is certainly something we are used to, right? That m plus 1 should be the same thing as 1 plus m.
Right. Any predictions for what's going to happen when we look at this more closely?
So I can try to normalize the goal a bit more. And it doesn't look good, right? Because I was really hoping that I would get 2 copies of literally the same thing here. Because that's when I can say REFL.
What happens if you...
So if I try to give REFL now, then I get this almost the same kind of problem I had with 17 and 42, right? That Agda is sure that these two things are not literally the same. And we see that n plus 1, that's what we had here. But actually 1 plus n has changed to something slightly different. That's the successor of n.
Yeah. If you do aggressive normalization on this goal, do you get as far as suck n? Yes, you do. Right. Yes.
And you have the same inequality.
Yeah.
So what is going on here? Well, what's going on, if we look at the definition of plus, so I can middle click on the plus symbol to go to its definition. Make this a bit bigger.
Right.
Then we see that plus is doing pattern matching on its first argument, right? So when we do 1 plus n, then 1 here is suck of 0. That's 1 plus m is going to be suck of n plus 0. And then we get stuck, right?
Yeah. So basically, Agda's approach to algebra is to hope that the free variables don't show up anywhere important. So in the case of 1 plus n, we get lucky. In the case of n plus 1, we're unlucky.
Because you see here, there is no equation that talks about n plus 1. Right? There's no 1 here in the second argument. It's only what happens when the first thing is more specific. So what we have to do in this situation is we have to make it get unstuck ourselves. So the problem is that this n plus 1 is stuck because we don't know what n is. Right? So we just have to pattern match on n and see if that gets it unstuck. Match on n. And then I can look at the goal again. And now we see that here the goal is 1 equals 1, right? It's good. I know how to prove 1 equals 1. And here, we see that the goal, this has reduced a little bit, and this has specialized a little bit. So we see that both starts with a suck, and then we are left with the same kind of problem again. So if we do a recursive call, test3 of n, then we see that that kind of matches the finger in the middle. So now there's a few ways we can proceed. The cheapest way is to use some special support for this.
Yeah, have you done the pragma?
Ah,
Yes.
okay. Let's we do it the other way then. So let's take a step back. So what's going on here is that we have the same function applied to equal things, right? That should still be equal. Let's see if we can find this. X and y, which are sets. Function from x to y. And I have x and x prime and x
This is the ancient wisdom.
equals x prime. Then f of x should be f of x prime.
Once upon a time, there was a mathematician called Mr. Algorithm who realized that if you've got an equation that's true and you do the same operation to both sides of the equation, what you get is still true. This is called the method of balancing, or algebra.
This is called Phong in the standard library because it's saying that the function f is a congruence with respect to equality. Okay, so if we had this, then here I could say Cong suck something, and that would tell me that suck of something equals suck of something. That's a good first step. And now here, I'm left with the same kind of problem again, so I can do a recursive call on a smaller n. Let you do it. So, but now I have to define Kong, of course, right? So, see what the goal is. So I want to show that these two things are equal, and I know that these are equal. And now we get to the point that Guillaume was trying to make before, where we are given some evidence that two things are equal as input, right? And the way we deal with things that are given to us by input is we pattern match on them to see what they are.
Yeah.
What could P possibly be?
So, what use is it to know an equation? Well, it means you can substitute one side for the other.
So we see that we have to, if we are, another way to put it, we are given some input of this type. So it's enough to deal with all the constructors of this type, right? There's only one constructor called REFL. But if we now look at the goal, we see that because this constructor was REFL, that means that the x prime must have been x, because REFL only works when the two sides are the same, right? So we have, by pattern matching here, we have learned something about other inputs. We have learned that x is in fact literally the same as x prime, which has now simplified our goal considerably, right? Because now another REFL fits in this goal.
So it's the same deal as when we were pattern matching on vectors. There's a non-trivial piece of detective work to say, how could it possibly have been this constructor? What else can we deduce if we assume it was this constructor? What else can we deduce if we think this equation was proven by REFL? Well, it must be that x prime was x.
And here's an idea. If you want to see what's happening, so it's the same REFL, but it's not used at the same time. Yeah, we have it. Let's go.
Yes, x is out of scope. And you also need...
Yeah, but I wanted to show it as an argument to REFL, but because it's a parameter.
So
Okay. So the general moral of the story is that there's certain equations that are not obviously literally true, right? In the sense that just by applying all the equations you have, you're defining equations for functions, you end up with literally the same thing on both sides, right? And then typically what we have to do is we have to pattern match on the stack input to expose to Agda that this is nevertheless true, right? You just have to look a little bit deeper. So we see that it's true for 0 and it's true for successors. So then it's true for every n, right? Which is it's another way to say that we've done this by proof by induction on n. Right?
So it's marvelous, right? In first year, we teach you to program and we teach you to do proof by induction, and we wait till fourth year to tell you it's the same fucking thing.
Why don't we show a little bit more examples of such?
What? What you fancy?
Thinking associativity of ZipWeb. So maybe we need to start by looking at ZipWeb.
Associativity, what's zip with?
I've also checked.
Uh-huh.
It's French again.
Uh-huh. How do I even get hold of in what way can zip with be associative?
Well, so maybe Guillaume does it again.
Well, you can net ZipWeb.
Yeah, why don't you do it, Guillaume? You thought about it.
Yes.
Okay. So this is in the standard library, right? And you have the definition of ZipWidth, which is basically like the ZAP we said the other day, but
for two things.
a bit more general, maybe.
Who put that in the standard library? I know
He
why it's in the
didn't?
standard library. It's because Haskell programmers expect to find it.
Yeah, it's convenient.
It's not even remotely convenient.
So we are here.
It's enough that vectors are applicative, right? ZipWidth's been in Haskell standard library since long before applicative functors were invented, and that's why it's in the standard library. Agda has no such excuse.
Yeah, associativity is probably a bad name, but whatever. Right, so we saw a small proof by induction involving natural numbers, but of course it's not limited to natural numbers. You can actually prove properties of any of the functions. And for instance, in the coursework, we ask you to prove that some circuits have the meaning you expect them to have. You could see that as some kind of proof on the meaning function rather than the syntax, right? So it depends how you see it. Right, so I showed you ZipWeb, but I didn't discuss it actually, so that's bad practice. So we take in a function, and then we take in two vectors of arguments, and we return a vector of result.
What's a vector?
Yes.
Oh,
Yes.
Oh, yeah.
Vec is standard library for what we called list n last week.
Yeah. So we started with list, then we did list one, then it just made sense to call it list n, but then after it's called a vector.
Maybe click on it briefly so we can
Yes,
see it.
it's really the same thing.
What?
oh,
Showing you
yeah.
the definition. Yeah. So I'm
And
using Alt full stop to jump to definition by putting the cursor on the name and then.
and is this 2 colons or is it something else?
This is magic. So, no, but that's fine. If you remember, you can do Alt X. Alt X is a lot of things in Emacs, and then you can write describe. I think, and it gives you a pile of text, which who gives a But the to input part is the interesting one, telling you how it was written. But then you sort of get used to it, right? There's a lot of it's not just random names for these things, right? If it looks like a colon, backslash colon will probably get you it, or a list that includes it, right? If it looks like an arrow, backslash, dash, forward angle thing will probably give you the sort of the list of arrows. Actually, I can show you.
Yeah.
Or,
Real-active programmers have encyclopedic knowledge of all of the Unicode whitespace characters.
but so you can see it's like the list, right? So you have the empty one, which has length 0, and then you have cons. The only thing is that cons is this like weird Unicode character. Okay. And then what were we? It has disappeared. And then we're looking at zip width. So zip width takes a function, and then, as I was saying, 2 left of size n arguments, and then returns a list of results. There are, of course, n results, and they are the results of applying f to the first A and B, the second A and B, the third A and B. So it's consuming the 2 lists in lockstep, and we can see it in the pattern matching, right? If the first one is empty, the second one needs to be empty because the n is the same everywhere, and the results can only be empty. And then if the first one is non-empty, then the second one needs to be non-empty. And then we return the first value here, and we keep going with the rest. So that's zip width.
If the function is an implicit argument to that, right? It's not in the type signature, but it's still.
No, this
Oh, it's not named, but it is here.
Yeah.
Yeah, it is explicit. Yeah.
yes.
So you could write this if you wanted, but let's not modify the standard library just now. Because this is, and then we have replicate. Well, replicate tells you that if you know a natural number and you know value of type A, you can build a list of size n with that value, and you just basically copy it. Okay. And then what could we prove? Well, let's just prove something very silly. So if I have, no, that's not going to be good, is it? X, Y, 2 sets. X is an X. So you can see that Agda is very liberal in where you put the type annotations, whether you name things or not. So yeah, so here I know what the issues are going to be, so I'm preemptively putting some type annotation. Full says that if there's a name, but there is no type annotation attached to it, then you just figure it out. So it's the same as full in mathematics, right? You're saying full, and this is true. And then looking at the equation, you're like, okay, n is probably a natural number. That's just the thing that makes sense in context. So here I have x and y, and because Agda has infinitely many sets, like a tower of them, I'm saying it's the small ones. Like, don't worry, it's the small ones. So that takes care of that problem. If I didn't write this, I would get some complaints, probably. So if I just wrote it like that, you see I'm getting a bunch of yellow. Oh, shoot, there are not enough type annotation. So I'm saying these are small sets. This is fine, don't worry. Then I figure it out from context. At the moment, the rest of the goal is still a whole, so there's no context to make sense of it. So we don't know what it is. And then I have an x of type x and a y of type y. And I'm going to give myself an n. And again, it's figure it out from context. And of course, because there's no context, it's all yellow. But then what I want to say is that if I zip with f on replicate and x, replicate and y, it's the same as replicate and f, x, y. This is shocking. What the? Oh, the, yeah, okay.
Yeah.
Well,
Yes. You're missing some important information here.
So you can see it down here in the goal. You can see that Agda's figured out that f is a function of type x to y to something, because f is applied to x and y, and we know the type of x and y, they are big X and big Y, but there is nothing here that determines what the output type of f should be. And indeed, You just don't know, right?
Yes.
Yeah.
It could be X, it could be Y, it could be something.
A secret third thing, and it's actually going to be a secret third thing because we want to be as general as possible, right? So my strategy was bad actually, right?
Yeah.
It's not the X and the Y's that matters, it's the F, because it's morally mentioning everything, well, except for the natural number, that's going to be at play, right? It's taking you what the type of the first argument is, what the type of the second argument is, and what the type of the return type is. So this was actually the crucial thing to annotate, to give Agda just enough information that the rest you don't need to write it down. You can if you want to, and if you write something silly like this, for instance, it will complain that, okay, this is a weird not equal to thing, but it will check your work. If you state something and it's not true, it will tell you off, but the trick is that you don't even have to state it.
Yeah. Have you ever played Kerplunk? It's the game where you've got a load of sticks stuck through a tube, and there's a load of marbles being held up by the sticks. The game is to take turns to remove a stick, and the person who makes the marbles fall is the loser. Well, it's like what you do is you write too much type information, and then you try and delete stuff until something goes yellow.
And I think we will live like that
Yes.
because it's almost 11.
Yeah.
So you can have a look at it in the lab if you want, or we'll look at it tomorrow.
Yeah. Well, why don't you normalize this goal just
Oh.
to leave with one thought? Right. Just, yeah. Right. So you see, trying to normalize this goal doesn't make any difference. Right. So there's a question that you need to learn to ask yourself, because Agda probably won't tell you. And that question is, why is it stuck? Oh, what is it that is making this, both this left-hand side and this right-hand side, reluctant to make any computational progress? What's the obstacle to computation? There's something, yeah, Agda's approach to algebra is to do as much arithmetic as possible and then kind of trip any time a free variable gets in the way. So what's the thing that we don't know that we would need to know to take a step of computation? Because that's the thing your proof has to look at. So there's an intimate relationship between why computation isn't happening and what you need to do to overcome that when you do a proof. It's the thing to be aware of.
You're welcome to come to the lab and start on the coursework.
Yes.
Or if you still haven't installed Agda on your machine, we can help you with that as well.
Well, yeah, that's it.
But that's it. Yep. If you could hand in the 1-minute papers in a pile somewhere in the room, maybe at the front of the room rather than the back.